So, why do we care about edge devices? And that's gonna connect to um, what um, what Dan was talking about at the start of his talk. Um, so, edge devices are extremely important when it comes to um, defense and aerospace industry, which is what SightX is doing. If you if you operate on the edge near the sensor, you don't need to transfer these petabytes of large images that Dan mentions. Um, and actually you can't. If you look up on the Russian Ukraine front, you had a lot of you have a lot of communication jammers, and you can get very little to no information through. Um, you want to be real time in those applications, right? You don't want the latency of going over to your server and then getting a response. And you can utilize your proximity to the sensor to get the raw data. And so most of the thermal sensors can give you 12 bits, 14 bits, 16 bits of resolutions. And when you need to compress it, to send it away, you get only about 8. And also you can support um, um, platforms talking to each other without them needing to go to a central place to communicate. So it's always a struggle to put like the top tier state of the art models into these like low computation devices. Um, and it's and we want to put those state-of-the-art model to be as much robust as possible to the challenges. So I'm gonna start with some example. This is like I'm talking about Merlin. It's our aerial product, and it's a little showcase of what it can do. You see here a bunch of vehicles and people later in the parking lot in thermal imaging. And then you see a very interesting case of re-identification. A group of people is going into hiding. And when they come out, we want them to be able to resume their original identities. So this is some of the stuff that we're doing, and I want to talk about the pipeline. So what you saw here is it's actually not one model; it's a whole pipeline of models. First of all, you have the object detection model, which detects the objects in the image. Then you have the feature extractor and the ReID module where you need it, and it's all orchestrated by a multi-object tracker. So if you were to put all these models together with no optimization, you will be able to obtain about 1 frame per second if you're lucky on those low power chips. And with optimization, we are able to obtain about 15 frames per second, which is very important for the use case that we're talking in, and about the accuracy of the results. Obviously, you can't operate a tracker on 1 FPS. So I'm going to talk about 3 approaches on this talk. I'm going to talk about deployment, and then I'm talking about pruning and quantization. So deployment-wise, we mostly, if you're like me, before I joined the SightX, you were training PyTorch models on NVIDIA hardware. And usually you have the pre and post processing, the logic, and you have all the layers and operators. And this logic is converted through Torch script um, with LLVM to assembler code, which runs on your CPU. And the layers and operators are converted into cuDNN routines and running on CUDA on the device, maybe like a NVIDIA GPU that you're using, which is actually that's what's doing the heavy lifting. So in order to optimize this, you can first optimize the graph, and you can cut away redundant connection and compute constants beforehand, and then you can use the manufacturer SDK to compile into the target hardware. And if we're talking about NVIDIA here, that would be TensorRT. So I didn't do any changes to the model. The model stays as it is. I just compiled it differently, and I took Resonant 50, which is like a model we all love to manipulate, and I tested it on my computer. So without just running it vanilla PyTorch inference, it had about 10 milliseconds of latency, and we were able to cut it by almost half, just compiling it different, which means mapping the layers and operators to the CUDA kernels more optimally. So let's talk about now that I want to now I want some stuff that I want to manipulate the model a little bit. So first and foremost, I'm going to talk about pruning. Pruning is it's a method of creating submodels from existing models by removing some elements. It's from agriculture. Here you see Japanese method of pruning in trees, and it works similar way. So we have our neural network, which I can prune the synapses. This is called unstructured pruning, where I zero out the weights that I don't use. And I can prune the whole neurons and the synapses connecting it, which is called filter pruning, structured pruning, channel pruning, and it means removing whole filters from the feature maps. So most of the times, we see that for applications of when we want to save runtime, it doesn't really help to do unstructured pruning, because not all the backends know how to utilize this sparse structure that was created. I think only with the Orin and Ampere series for NVIDIA, they know how to utilize sparse tensors to accelerate the model. So structured pruning is basically the main method we use for pruning at SightX. So I'm going to explain briefly how it works. We have our model, we do forward pass, get the feature maps, and then we look at the channels and see what what feature maps are not so important, and then we just remove them, and we get the out channels, and we do a little bit of training, and then back again, and the process stops. Either if we're satisfied about, I don't know, maybe it's the size of the model, maybe it's the latency, or I've dropped my performance more than I wanted, right? Let's say, I don't know, drop 3% accuracy on the ImageNet. So this is the general schema, and then so how do we prune those feature maps, right? I said that we prune the least important, but how do we know? Well, a lot of times we look at the values, like L2, L1 norms, and prunes those out. But a lot of research has been done, and these are interesting papers for me on this field. I divided them into two categories. One is the filter ranking, which is methods for trying to find out how important this feature map that I'm about to prune is. And the other group is a pruning method. It's maybe I have changes to the general algorithm of pruning itself. So I'll touch each one of those very brief. I'm going to talk about only the main principle in each paper. So Taylor expansion, this formula here, you probably didn't see it since I don't know, your graduate degree. It's the same expression here, only in respect to the channels. The main idea is, what if not only the values of those feature maps count? What if you need to also, what if the gradient also plays a major role here? You don't want to prune a layer that's giving you very big gradients. So this was able to improve results right off the bat. HRank, I really like this work because it's really simple. You're taking the feature maps and you're looking at them like matrices. And as we know, the rank of the matrix really determines how compact in information the matrix is. So might be that you don't want to prune matrices that are feature maps that are compact with information. And what I like about this, and this is the images you see here, that they proved, or not proved, they showed in this paper that the rank doesn't change, and it's not really dependent on the mini batch. So they took Resnest 56 and this is snapshots from the first layer, the middle layer, and last layer. Oh, sorry. And on the x-axis, you have the index of the feature map within the layer. And on the y, you have the batches. So this is the rank for one batch. This is the rank for 5 batches all along to 50 batches. And the value is denoted by the color. So you can see that even with one batch, it's one mini batch is 128, I think, in this paper. You can really predict very well the rank of all the feature maps in the model. So you don't need to go through iterating all your data through. Channel independence. So these two methods were really about each individual feature map. And channel independence is more about, they got the hypothesis of how can I be sure that I'm not pruning a unique feature map. So what I want to do here is I want to, instead of maybe calculating importance, the importance of a channel in and of itself, I'm going to take all the channels within the layer, and I'm going to do something that's measure how each respective channels are behaving in relations to each other. So they took all the feature maps within the layer, they flattened it and put it as row in a matrix, and they kept omitting one row and calculating the nuclear norm, which is the sum of the singular values. And if I had a major drop on the nuclear norm, it means, okay, it's something important. All these are great, and we're arriving at the second method. So what I liked about this paper, about the knapsack pruning, is they had a different perspective of looking at the problem. They said, okay, let's, if I have a threshold of flops or a latency that I need to keep in, what are the most valuable pieces I can have that abide by this latency? So this is so I want to satisfy. They took each feature map and they calculated the difference in loss and the contribution in flops, and then you have and then you can build your model like Lego pieces with the right ones. Finally, you have the channel exploration, which in this paper they said, okay, we got it. You pruned a bunch of feature maps, but what about letting a chance to grow ones? So if I heavily pruned, they designed a system that if I heavily pruned a layer, I'm able to grow another layer, the synthetically added, that has the most common values from the layers I prune, essentially giving a chance for this intermediate representation and see if it fits. So for our applications, and we checked all of those, and we did our own variations. HRank really helps because it's fast, it's lean, it's not complicated, and you can prune 30% of your redundant feature map with HRank. And this is something you can do just to get you going. Then you need to combine. We're combining the Taylor expansion and the channel independence, along with the size with different weights, in order to see how important um, a feature map is. Actually, something interesting happened with the channel independence. Um, we didn't have improvement when we first tried to play with it, but once we got it into our loss function, essentially telling the model, okay, this is important. You should try make your channels within the model. You should try to make them independent. Then we see it. So we saw like a major boost in it. And knapsack pruning, we started doing it. It's not that useful because it's very computationally expensive. Think about doing the ranking for each submodel for each iteration you prune. And the channel exploration, in my opinion, should give us better result, but we're still looking at it. It wasn't able to improve our result. So we did all this work of combining these different technique and integrating them and maybe elaborating on them, and I want to see what happened to our Resin 50 model. So this time I ran it not on my computer, on Xavier NX. This is using the TensorRT, the one I showed earlier. And it had a latency of 50 milliseconds. And then we pruned the hell out of it. We pruned about 75% of its weights from a model of 25.6 parameters. It shrunk down to 6.4 million parameters. And we dropped the latency by half, which I think is pretty impressive. So it's just to show you that pruning is really, really useful. But sometimes, it's you need to. There are some stuff that you need to pay attention to. This is just I took a random photo of efficient architecture, and here you see the backbone and the neck and the head, and each model within this detector has different meaning of pruning the layers, right? You wouldn't be able to achieve good result if you pruned if you treated layers here the same as layers in the backbone. So especially like if we're talking about the detectors which are anchorless, like YOLO-X, if you prune a feature map, you essentially pruning the anchors. So it has different meanings. What we're usually doing is pruning it by parts. We're first pruning the backbone, then freezing it, then pruning the neck, and then the head, and so on. We do it also for generative models, and it works really well if you stay within the model. And those of you who are using transformers, pruning, all the methods I mentioned are not very useful for transformers. But I won't get into that. So let's talk about quantization. Quantization is very widespread. It's computing it's be able to do computations in lower resolution, bit resolution. So most of the times we see the baseline is floating point 32. We see quantization to 16 bits, 8 bits. We have mixed precision, which is I'm going to do the whole thing in 8 bits, but only certain operation in 16 bits and so on. And now, because of the LLM, the LLM movement really gave it a boost, because now you're able to see not only quantizing to 4 bits, you can see people training in 4 bits, which is crazy to me. But this way you're able to get these very big models and train them using a very simple hardware. So I'm not gonna get really into quantization, just things that worked for us. When you quantize, when I first tried to quantize, I was very tempted in using all those very cool mappings of the quantization values. And then I discovered that you need to do for float 16, it's fine, but if you go into 8 bits, you need to do a lot of transformation back and forth from 8 to 13. And if you're using very unique kernels, then it's going to cost you that latency you were trying to get. So linear mapping is the way to go. We also started to see when we talked about compact feature spaces, and it actually makes a lot of sense. If you have very compact feature spaces and you want to distinguish between clusters within that feature space, let's say for a rate identification task, you wouldn't want you will want the whole resolution in this feature space. Also, if you're trying to when we did the simulative data using generative models, same story. You need to be able to get a lot of variance, and you can do it in a low resolution. And lastly, quantize-aware training really does the trick for us. This way, you don't need to have most quantization algorithm, and they require a calibration set. This way, you can just save the cutoff values for each individual layer, and it saves you that, and you really can reduce the quantization error by using it. So to conclude, we have this graph here. Here is the unpruned model is in blue, the pruned model is in red. And you can see three different quantization. One is the original 30 floating point 32. This is a 16-bit in the 8 bits. And we were able to go down from the initial 33 milliseconds with pruning and quantization to about 5. I remind you that if we were not using the TensorRT, this would be higher by a factor of 2. So really big acceleration factor in terms of latency, with very little degradation comparatively. So I think that's it. I see we have a bunch of questions in the Q&A.
Yeah, so if you want to go ahead and tackle those.
Yeah, sure. Can I mention any families of embedded processor? Okay, so we're working with, of course, NVIDIA, and we also work with Intel, Halo, Qualcomm, the Snapdragon, as early as 820, and probably the new series of the Qualcomm Snapdragon and the Halo are showing the most promise for us. It would be quite interesting to know what sort of feature extraction you use and do those front-end change with application. So, okay, we do use different architectures of feature extractors. And if they change with application, yeah, it really depends. If you're trying to do short-term feature extraction just for okay, so we seen this group of people going into the behind the bushes and going out. This is short-term occlusion, so you don't really need a very good or a very deep feature extractor because you're trying to identify them. Maybe 30 seconds later, they're the same angles, the same perspective. But if I'm looking at two different directions, or I'm trying to identify the same object 1 hour later, maybe they change clothes, maybe they put down a backpack, then I will be doing a much deeper feature extraction. Have you done any comparison between efficiency obtained by pruning versus reducing the dynamic range in terms of resolution? Oh, this is the quantization versus pruning. Yeah, we felt that quantization was able to give the bigger boost, but a factor of 2 is not something we take lightly. We're really happy with doing structured pruning. Since you're essentially doing feature selection, you might actually expect increase of performance. Have you seen performance improve as you remove feature incrementally? Well, there is on the first few steps, I've seen performance slightly increase, but then it's decreasing because you're really biting into those features that the model is using. As you saw in the example, I cut down 75% of the model weight. It's a really much smaller model than I started with. Does the pruning cause some negative impact to the accuracy of the model? Well, of course. Another, I showed it, I think, previously here. Yeah, I mentioned it here. I had, no, this is okay. So where we pruned, the accuracy was reduced by the top 1 accuracy was reduced by 2%, and the top 5 was reduced by 1%. But I think that's price I'm willing to pay for the 50 for the factor of 2 in latency boost. I will mention that we also use teacher-student knowledge distillation from the original model that was mentioned. That was what they did also in the knapsack, and it was able. It allowed us to mitigate this accuracy gap a little bit. Next question. Can you use an auxiliary network like SVM to use recursive feature elimination based on feature coefficient magnitudes to rank all your features for iterative removal? Wow, that's a great idea, actually. We tried to find, we try to find robust methods that are also very fast, because you don't want to think about it as an iterative step. You don't want to really take I don't know, twice the time to train your model. But I will. It's an interesting question. I will look into it. So are you saying the wrapper methods are just too computationally expensive to be practical? No, I didn't say that. I just said that especially just with the knapsack pruning. So you're trying, the first component is the difference of the loss. So think about computing differences of losses for each individual feature map, for each iteration, right? Because you do the first few, you prune the first few layers, and then you have a different model. You need to compute the loss difference again, and it's this is very computationally expensive. The channel exploration, not so much, but the channel exploration doesn't. To me, it looks very promising. I really like the idea, but currently we're not able to. It didn't improve on our previous methods. Which one is better, pruning or quantization? To that, I'll answer: why not both?
All right. Fantastic. So I think
thank you very much.
I think that's it. So thanks again, Roz, for presenting. It does look like we have one last one, if you want to do the bonus round.
Oh, of course. Can we use them for face recognition model training as when we try to do it on real-time camera? It's so bad. You can, so in terms of when we use those techniques, so pruning is used after we do it after we train the model, the structured pruning, and then you actually train it more, right? Because you meet those channels and you need to do the training step. And quantization, we also compute just the cutoff values, because that's all you need for linear quantization during training. And then when I go ahead and compile the model to lower bitrate, then you use those values that you already computed. But you can do post-training quantization using a calibration set. Usually you'll get the boost from 32 to 16 with little to no performance degradation. But when you jump from 16 to 8 bits, you're gonna suffer a lot if you choose a poor calibration set.